Welcome, welcome student to online lecture series of Chhatrapati Shivaji Maharaj College of Engineering Nepal. Our subject is microprocessor and the topic of today's lecture is virtual 8086 mode. This is the third part of our unit 5. So these are some contents that we will see throughout the lectures, that is virtual 8086 mode, executing 8086 code, structure of V86 task, entering and leaving virtual 8086, that is V86 mode. So let's start with first virtual 8086 mode. The 80386 supports execution of one or more 8086, 8088, 80186 programs in an 8086 protected mode environment. An 8086 program runs in this environment as a part of virtual 8086 task. The V86 task takes advantage of hardware support and multitasking offered by the protected mode. The purpose of V86 task is to form a virtual machine with which to execute an 8086 program. A complete virtual machine consists not only of 80386 hardware, but it also supports system software. That is, the complete emulation of 8086 is a result of cooperation between hardware and software. The hardware provides a virtual set of registers, a virtual memory space, and directly executes all instructions that deal with these registers. The software controls the external interfaces of virtual machines such as input-output, interrupts, and exceptions in a manner consistent with the larger environment in which it executes. In the case of input-output, software can choose either to emulate I/O instructions or to let the hardware execute them directly with software intervention, that is, without software. Then next, executing of 8086 code. The processor executes in V86 mode when the VM bit, that is virtual machine bit, in flag register is set. That is when VM is equal to 1. The processor tests this flag under two general conditions. First, when loading segment register to know whether to use 8086 style address formation, and second, when decoding instruction to determine which instructions are sensitive to input-output revision level, that is IOPM. Except these two conditions, that is registers and instructions and linear address formations, all others are work in V86 mode in protected mode of 80386. So let's see registers and instruction first. Registers and instructions. The register set available in V86 mode, that is virtual 8086 mode, includes all the registers that are defined by 8086 and plus the new registers that are introduced by 80386, such as FS, GS, the segment registers, debug registers, control registers, and test registers. These new instructions that explicitly operate on segment registers, that is FS and GS, are also available, and the new segment override prefix can be used to cause instruction to utilize FS and GS segment registers for address calculations. 8086 programs running as V86 tasks are able to take advantage of new application-oriented instructions added to the architecture by introduction of 80386, such as single bit instruction, bit scan instruction, double shift instruction, byte set on condition instructions, generalized multiply instructions, and move with sign or zero extension. Then linear address formation. In V86 mode, the 80386 processor does not interpret 8086 selector by referring to descriptor. Instead, it forms linear address just like 8086 microprocessor. For that, it shifts the selector left by 4 bits to form a 20-bit base address. The effective address is extended with 4 high-order zeros and added to the base address to create a linear address. Because of the possibility of a carry, the resulting linear address may contain up to 21 significant bits. Therefore, 8086 program may generate linear address anywhere in the range of 0 to 10FFF Also, V86 task generate 32-bit linear address while an 8086 program can only utilize the low order 21 bits of linear address. The linear address can be mapped with the help of page tables to any 32-bit physical address. Unlike 8086, 32-bit effective address can be generated. However, the value of 32-bit address may not exceed 65,535 without causing an exception. For fully compatibility with 80286, real address mode occurs if an address is generated outside the range of 0 to 665,535. This diagram shows how the base plus offset is converted to form a linear address in virtual 8086 mode. The next structure of V86, that is virtual 8086 task. A V86 task consists of partly of 8086 program to be executed and partly 80386 native mode code that serve as a virtual machine monitor. The task must be represented by 80386 TSS. The processor enters V86 mode to execute the 8086 program and returns to protected mode to execute the monitor or other 80386 tasks. To run successfully in V86 mode, an existing 8086 program needs V86 monitor and operating system services. The V86 monitor is 80386 protected mode code that execute at privilege level 0, that is PL0. The monitor consists primarily of initialization and exception handling procedure. As for any other 80386 program, executable segment descriptor for the monitor must exist in GDT, that is global descriptor table, or in the task LDT, that is local descriptor table. The linear address are available for the V86 monitors, the operating systems, and other system softwares. The monitor may also need data segment descriptor so that it can examine the interrupt vector table or other part of 8086 program. In general, there are two options for implementing the 8086 operating system. The 8086 operating system may run as a part of 8086 core. This approach is desirable for any of the following reasons. The 8086 application code modifies the operating systems, and second, there is a not sufficient development time to re-implement the 8086 operating system at 8086 core. The 8086 operating system may be implemented in V86 monitor. This approach is desirable for following reasons. First, operating system function can be more easily coordinated among several V86 tasks. And second, the functions of 8086 operating system can be easily emulated by calls of 80386 operating system. Then next is operating system services. Paging for V86 task and protection with V86 task. These two services are provided to V86 mode for with the help of operating system. So let's first using paging for V86 task. Paging is not necessary for a single V86 task, but paging is useful or necessary for any of the reasons, that is to create multiple V86 tasks. Each task must map the lower megabyte of linear addresses to different physical locations. Second, to emulate the megabyte tracked on members of 8086 family. It is possible to specify addresses larger than 1 megabyte. Then third, to create a virtual address space larger than the physical address space. And fourth, to share 8086 OS code or ROM code that is common to several 8086 programs that are executing simultaneously. And last, to redirect or track references to memory map IO devices. Then second one is protection within V86 tasks. The second services that provided by operating system to V86 to protect the system software that runs in V86 tasks from 8086 program. Software designer must follow these approaches. First, reserve the first megabyte of each task linear address space for the 8086 programs, and 8086 tasks cannot generate addresses outside this range. Then second, use the US bit of the page table entries to protect the virtual machine monitor and other system software in each virtual 8086 task space. When processor is in V86 mode, CPL is 3. Therefore, an 8086 program has only user privilege. If the pages of the virtual machine monitor have supervisor privilege, they cannot be accessed by 8086 program. Then next, entering and leaving from V86 mode. As shown in figure, there are two possibilities, that is task switch and interrupt and exception gate that causes the 8086 program to enter and leave from 8086 program to other programs. A task switch to an 8086 task loads the image of flags from new TSS. The TSS of the new task must be an 80386 TSS. A value of 1 in VM bit of the new flag indicates that the new task is executing 8086 instructions. Therefore, while loading the segment registers from the TSS, the processor forms base address as same as 8086 microprocessor. Then second, an I return from a procedure of 8086 task loads the image of flags from the task. A value of 1 in VM bit in this case indicate that the procedure to which control is being returned is an 8086 procedure. The processor leaves virtual 86 mode when an interrupt or exception occurs. There are also two cases. First, the interrupt or exception caused the task switch from V86 task to an other task loads flags from the TSS of the new task. If the new task is an 80386 TSS and the VM bit in the flag register is 0, or if the new TSS is an 80286 TSS, then the processor clears the VM bit of flag registers and loads the segment registers from the new TSS using 80386 and begins executing the instructions of new task according to the 80386 protected mode. And second one, the interrupt or exception vectors to a privilege level 0 procedure. The processor stores the current setting of flags on the stack, then clears the VM bit of flag registers, and then the interrupt or exception handler therefore executes an 80386 protected mode code. If an interrupt or exception vector to a conforming segment or to a privilege level other than 3, the processor causes a general protection exception. That is, the error code is the selector of executable segment to which the transfer was attained. So let's see first transition through task switch. A task switch to or from V86 task may be due to any of the three reasons. First, an interrupt that vectors to a task stage, task gate. Second, an action of a scheduler of 80386 operating system. Or third, an I return instructions when the empty flag is set. In any of these cases, the processor changes the VM bit in flag register according to the flag registers of new TSS. If the new TSS is an 80286 TSS, the high order word of flag is not in the TSS. The processor clears the VM bit in this case. The processor updates VM prior to loading the segment register from the image in the new TSS. The new setting of VM determines whether the processor interprets the new segment register image as 8086 selectors or 80386 selectors. Then second, transition through trap gate or interrupt gate. The processor leaves V86 mode as a result of exception or interrupt that vectors through a trap or interrupt gate to a privilege level 0 procedure. The exception or interrupt handler returns to 8086 code by executing an I return instruction because it was designed for execution by an 8086 processor. An 8086 program in V86 task will have an 8086 style interrupt table starting at linear address 0. But in 8086, it does not use this table directly. For all exception and interrupt that occur in V86 mode, the processor vectors through the IDT. The IDT entry for an interrupt or exception that occurs in V86 task must contain either a task gate or 8086 trap gate. Interrupt and exceptions that have 80386 trap or interrupt gate in IDT vector to the appropriate handler procedure at privilege level 0. The content of all 8086 segment registers are then stored on the PL0 stack. After the processor stores all the 8086 segment registers on the PL0 stack, it loads all the segment registers with zeros before starting to execute the handler procedure. This permits the interrupt handler to safely save and restore the DS, ESFS and GS registers as 80386 selectors. Interrupt handlers that may be invoked in the context of either a regular task or a V86 task can use the same prologue for register saving regardless of kind of task. Restoring zeros to these registers before execution of IRET, that is iReturn instruction, does not cause a trap in the interrupt handler. Interrupt procedures that accept values in the segment registers or that return values with the help of segment registers have to use the register image stored on the PL0 stack. Interrupt handler that need to know whether the interrupt occurred in V86 mode can examine the VM bit that is stored in flag registers. An interrupt handler passes control to V86 monitor if the VM bit is set in the flag register that is stored onto the stack, and the interrupt or exception is one that the monitor needs to handle. The V86 monitor may either handle the interrupt completely with the V86 monitor or they invoke the 8086 program interrupt handler to handle that interrupt. So this will end our last topic from Unit 5, that is Virtual 8086 mode. Thank you for watching. Please subscribe our college channel